Just wanted to thank everybody for showing up today. I saw that Damian had retweeted the YouTube link. So we had lots of people on YouTube tonight. That's great. Thank you for doing that. And, we do these meetings every month, and we have great speakers from literally all over the world. And Shannon has been bugging me, Shannon, how long have you been a member now?
4 years.
4 years. So he's been a member for 4 years, and we've never had an astrophotographer yet as one of our speakers. That's a lot of speakers with no astrophotographers. So we've got two great ones coming up, obviously, tonight. And then on May 18th, as we mentioned earlier, Thierry Legault will be here. He'll be in from France. So these guys, we're keeping them up awfully late tonight. And can't wait for those. So again, thanks to everybody on YouTube, the Zoom conference tonight, the live stream, and everybody that came from Meetup too. So the introduction of our speaker, Damianpeach. He is a British amateur astronomer, astrophotographer, lecturer, and author. You've seen his stuff everywhere. His career, believe it or not, for his age, he's been doing this for over 30 years. And back in 2017, he formed part of a small team of observers who used the Pic du Midi Observatory. It's a 1.06 meter telescope to obtain some of really the most detailed ever ground-based images of Jupiter and Saturn. And then that same year, the asteroid 27632 was renamed Damianpeach by the International Astronomical Union for his contributions to amateur astronomy. And in 2018, he was elected to the board of the Aster Academy Scientific Committee and also awarded the Astronomical League's prestigious Peltier Award, again, for his contributions to astronomy. So without further ado, please welcome Damianpeach to the March 2021 free Westport Astronomical Society Science Lecture Series. Mr. Peach.
Well, thank you, guys. So, tonight I'm going to be speaking to you about high-resolution astrophotography, specifically planetary imaging, which is something I've spent the vast majority of my career in. And planetary imaging is, as I mentioned during the early part of your presentations, it's one of the more challenging areas of astrophotography, as I'll come to explain as we go through the course of this talk. And during this presentation, I've included a wide variety of material from stuff for beginners, so fairly rudimentary information, through to more advanced advice. But hopefully there's some information during the course of this presentation that many of you will find useful to help improve your own imaging and techniques. So to begin with, just to cover some fundamentals of high-resolution imaging, one of the key things to consider is that larger apertures are able to resolve finer detail than smaller ones. So, for example, you can see here two images of Saturn presented, one from a 10 centimeter aperture, one from a 40 centimeter, and obviously the larger aperture telescope is able to resolve much finer detail. And you can see here also some simulated star images from apertures of different sizes, 10 centimeter at left through to 40 centimeter at right. So you can understand here how larger telescopes are able to resolve finer detail on planetary targets than smaller ones can. But of course, it's not that simple, because we were also having to contend with looking at astronomical objects through Earth's atmosphere, which, as you come to see later on, is probably the single biggest limiting factor in how sharp ground-based astronomical images can be. You can see here some simulated views of extra and intrafocal star images and Saturn, with increasing amounts of atmospheric turbulence imparted into the views. And you can see that even with very slight amounts of atmospheric turbulence, the sharpness of the planetary view starts to degrade quite noticeably. So you can understand how turbulence within Earth's atmosphere is really a major factor in how sharp and detailed the images of the planets that we can get are from ground-based telescopes. And just to go over that in some more detail, you can see here, for example, we've got a simulated 10-inch aperture telescope of very high quality with 30% obstruction. And you can see there, with no atmospheric turbulence, would deliver a really nice sharp view. If we impart just a tiny amount of 0.15 waves RMS of atmospheric turbulence into the view, which, as I say, is a very small amount, this would still be good seeing. You can see even with that very small amount of turbulence, the view is already starting to degrade. So just to kind of hit that point home, atmospheric seeing really has a major effect on image quality. Now, one of the big questions that always comes up, and I've been asked countless times over the years when it comes to doing this kind of astrophotography, is what is the best type of telescope to be using for doing this kind of imaging? And there are various points that you can see that I've noted on this slide, but there are maybe some key points to make here. And that one I would say is that if you're a beginner, so just starting out and finding your feet with it, it's probably best to start with a refractor, because they typically can work really well straight out of the box with minimum effort in setup and preparation. If you're slightly more experienced, it's definitely better to be using larger aperture reflectors, such as a Newtonian or Schmidt-Cassegrain. They're typically the most popular choices. But of course, they require more attention to things like collimation, which I'll talk a bit more about in a moment, and also cooling. And another key point to consider is choosing a telescope that you can use easily and frequently. So if you're in the position where you have to set up your telescope each time you observe, I would always err on the side of going with something that's easily portable. So if you're just buying a really huge telescope and you have to set it up each time, trust me, it will kill your enthusiasm in the long run. So it's always better to have something you can use easily and frequently. Now, my own two primary telescopes that I've used for the majority of my career, Celestron C14 Schmidt-Cassegrains, and one I have stationed overseas permanently on the island of Barbados, which is located in the Caribbean region, which benefits from low latitude and frequent excellent seeing conditions. And I also have another one here at home for use in the UK, which is the more modern Edge HD version. During recent years, I've also been fortunate to observe remotely as well. And over the last 3 to 4 years, I've been using this telescope, which is a 1 meter Ritchie-Chrétien telescope located in Chile, which is part of the Chile Scope Observatory. And as I say, I've been using that quite extensively over the last 3 to 4 years, observing remotely. So that's been particularly enjoyable. And as I've also mentioned there, this telescope can actually be booked online for use for planetary imaging via the chilescope.com website. So just moving on to talk a bit more about some of the key issues when it comes to high resolution imaging. Collimation is one of the vital issues when it comes to reflecting telescopes in particular, and that is achieving the proper alignment of the optical elements of the telescope to deliver a sharp image. And here you can see a kind of basic guide to gauging the collimation of your telescope. So you can see here, step one, we've got a low power view of the star out of focus, and what you'll see is a bright donut shape with a hole in the center. And if that hole is offset to one side, you'll need to adjust the collimation of the telescope using the primary or secondary collimation screws, depending on the type of telescope you've got. The next stage is to move to higher power evaluation. And I should point out here that step one is nowhere near good enough to properly collimate a telescope accurately. So, for example, it may look collimated at low power, and you think, yeah, that's good enough. It isn't good enough for doing this kind of imaging. The telescope needs to be collimated very accurately. And that can only be achieved at high magnifications and under good seeing. So as we move the power up, You can see that I've noted around 500 times. And we defocus the star much less. We can see much smaller misalignments that can be corrected. And you can see here two views, one at left with the telescope in accurate collimation, one at right with it slightly out. And again, you'll just be making a very slight adjustment to the collimation screws. And what you're trying to do is to get that looking like a bullseye. So a nice concentric bullseye pattern. At stage 3 can be an in-focus high power evaluation if the scene is very good. And you should have a nice airy disk visible through the eyepiece. And there are some other points I should make when it comes to collimating as well. And you can see here I've noted some various things to consider. And obviously taking your time with collimating, don't rush it, it is important. And also it's, you know, not a once every year process. It's something to be checked regularly to make sure the telescope is retaining collimation as well. Also, when selecting a star for collimation, use a star at least 45 degrees above the horizon, so not something too low down. And if the target planet is lower, always use something a bit higher above the horizon to get above the worst of the turbulence. And also make sure it's bright enough as well, so around first to second magnitude is fine. Another important point to consider, particularly for Schmidt-Cassegrains on German equatorial maps, is if you're moving the optical tube from one side of the mount to the other as it crosses the meridian, you typically need to recollimate the telescope. And often Schmidt-Cassegrains, particularly large aperture ones like the C14, do not hold collimation when switching from the east to west side of the mount and vice versa. So that's something to keep in mind. As I've mentioned already, using high powers for really accurate evaluation of collimation. And if you don't want to do it visually, and I should say that over the years, I've kind of always collimated visually at high powers, as I just kind of, you know, I've done it so much over the years, I've kind of become really attuned to it. But you can also use the camera itself instead of the eyepiece to collimate. And this can be a really good way to collimate accurately. Because this also allows you to use filters to help with atmospheric turbulence. So using a red or near infrared filter when collimating can help improve the view, as long wavelengths are much less affected by turbulence. So this can be quite a good way to collimate. So having covered collimation, I just want to talk a bit more about one of the other really important issues when it comes to telescopes, and that's cooling and thermal considerations. And it's really, really important that the telescope you're using for planetary imaging is at thermal equilibrium with the outside air. And you can see here some real star images from telescopes that are not at thermal equilibrium from the outside air. And I'm sure many of you have seen weird distortions like this yourselves in out of focus star images through telescopes. And these are a clear indication that the telescope is not at equilibrium with the surrounding air. And the larger the aperture is, the more time it takes to cool down. And I'll go as far to say that telescopes above 10 inches aperture probably need to be kept outside permanently to really allow them to reach thermal equilibrium properly. And larger apertures, it's absolutely essential for them to be kept outside. Otherwise, they'll simply never cool down. So here you can see a real video of an out of focus star through a telescope that's not at thermal equilibrium. So that fast jittering that you can see is the result of atmospheric turbulence. But those very slow moving distortions that you see in the out of focus star image there are the result of thermals within the telescope itself. And these can have a seriously debilitating effect on image quality. And basically, you end up with the telescope performing as, you know, say you've got a 10-inch telescope, it might be performing like a 5-inch telescope in terms of its resolving capability. It's a very, very important thing to consider. So as I mentioned there, don't overlook thermal. and cooling issues that are so important, particularly for large telescopes. Some designs are better than others, particularly from temperate climates where you can get a big temperature swing from day to night at certain times of year. But generally, large aperture max shoot-offs are best avoided, particularly above 10-inch aperture, as they can really struggle to reach thermal equilibrium. As I mentioned, larger telescopes need to be kept outside, really, to give them every chance of reaching thermal equilibrium, and also consider a more active approach to cooling. So you can install cooling fans and cooling systems on telescopes, or using ice packs and things like that to cool the optical tube. And this can really help to deliver good image quality. And this image of Jupiter here, which was taken on April 23rd, 2015, literally just after sunset on a spring evening where the temperature had dropped rapidly. And this was taken using the Celestron C14 Edge HD optical tube. And this image was only possible because during the day, I dismounted the optical tube, put it in a sheltered position when no direct sunlight could hit it, put several ice packs over the tube and just left it there during the day. As sunset approached, I then remounted the optical tube, and it's that attention to cooling the optical tube during the day. And when I remounted the tube, quickly checked the collimation, the telescope was perfectly at thermal equilibrium with no thermal distortions in the star pattern. And it's that attention to having cooled the optical tube that allowed a Jupiter image like this to be obtained. Now, had I just left the optical tube mounted and left it to heat up during the day in the sun, there's just no way on earth I would have been able to obtain an image of this quality. So very important to pay attention to cooling and thermal issues. So just moving on from that to cameras, and the kind of cameras that we use for high resolution planetary imaging kind of somewhat different to what you would use for deep sky, in that what we're doing is taking high-speed video sequences. And the cameras that you can see here basically hook up to a computer, the USB 3, and allow you to take high-speed video sequences at around 100 frames per second. And there are various manufacturers that produce these cameras. These are the most popular models available, such as ZW Optical, QHY, and Point Grey, which is now FLIR, and DMK. And these cameras all basically do the same thing. As I say, they take high-speed video sequences. So just to move on from cameras to focusing. And again, this is another really important thing to consider when it comes to high-resolution planetary imaging. And one thing I would say immediately is that if you don't have a motorized focuser on your telescope, this is, I would consider, an absolutely essential piece of equipment to add to your telescope for doing this kind of astrophotography. Simply focusing with a focusing knob for planetary imaging is just woefully inadequate. You need to have a focuser that allows you to focus the telescope without having to physically touch. And you can see there right is a motorized Crayford focuser with handset, and this can fit onto the back of a Schmidt-Cassegrain, and it allows you to focus the telescope very accurately without the need to physically touch the telescope or touch the focusing knob of the telescope. Now, when it comes to focusing on planetary targets, what I generally do, I always focus on the planet itself. So I don't slew off to a star, focus on that, and then go back. I use the areas of good contrast on the planet itself to judge the focus. So with Saturn, we've got the Cassini division in the rings. With Mars, you have the albedo markings or bright cloud features and polar cap, or indeed the edge of the disk. With Jupiter, the most prominent cloud features on the disk are the best gauge of focusing. And as I say, they are always the best things to use for gauging focus, and it's just a case of getting used to the focusing system you're using. And another point I would also make is that focusing in good seeing is far, far easier than poor seeing. So when you have a really good steady night, you'll find it's actually relatively easy to hit proper focus. Whilst if the seeing conditions are not good, focus can be quite a frustrating process, as you're often going back and forth, trying to find a good focus point. So just to move on to another piece of equipment that many of you will find of great use, particularly with Jupiter and Saturn at the moment due to their southern declination, and that's an atmospheric dispersion corrector. And this small device fits onto the focus end of the telescope and basically corrects for atmospheric dispersion, which is the smearing out of light into its constituent spectrum by Earth's atmosphere. And Earth's atmosphere basically acts as a lens, so the further you get from the zenith, the worse dispersion becomes. So there's zero dispersion at the zenith, and as you move towards the horizon, it gets worse and worse as the altitude of the planet becomes lower. And this device basically corrects for that. Now, you can see here just a typical dispersion corrector available from ZWO Optical, and you can pick one of those up for around $130. And as I say, it's a really, really worthwhile piece of equipment, particularly for Jupiter and Saturn at the moment from the Northern Hemisphere. And here you can see just a typical example, an image of Mars at 30 degrees with no dispersion corrector. And with the planet at 70 degrees above horizon, you can see there's almost zero dispersion. And using the dispersion corrector will completely remove that color fringing that you see and give you a much sharper image. So actually, I would just say, before I move on to the next slide, that if you're using a color camera, so obviously the cameras that you can get to come in one-shot color or mono, if you're using a color camera, a dispersion corrector like this, I would consider an absolutely essential piece of equipment. So just to move on to capture software, by far and away the most popular piece of capture software for operating these video cameras is Firecapture, and it can be downloaded from the link that you see at the bottom. And this piece of software, as I say, by far and away the most popular piece of software available for operating these cameras, and it supports almost all of the cameras that you can think of. And it has various different settings, as you can see in this screen here, such as gain, exposure, and all manner of different things that can control all of the different features of the video camera. And just to give you a few kind of fundamental tips on capturing image sequences with Firecapture. So typically you capture in video AVI or SER sequences, and these typically consist of around several thousand frames during the course of a capture. So with the ASI, ZWO ASI series of cameras, it's always best to leave the gamma setting at its default value. When you start playing with that and capturing data with it set too low, for example, you can end up with all kinds of weird artifacts in the data that you'll struggle to get rid of. So it's always best to leave that at the default value. When it comes to planetary imaging as well, don't set the camera gain to a very low setting, as again, this can result in all kinds of weird artifacts around the limb of the planet that you'll struggle to get rid of in processing. And it's always best to have the gain set around 60, 70%, somewhere around that point, and adjust the exposure time accordingly. For Saturn, I would say we need to use higher gain because its surface brightness is much lower. So typically with Saturn, we can be shooting at 90% gain and just collecting more data. And of course, Uranus and Neptune being much fainter still, typically need near maximum gain. And again, just collecting many more frames over a longer time period to combine together. For those shooting through with mono cameras and RGB filters, typically the best methods are shooting repetitive RGB sequences. And of course, if you're imaging, if you're not using processes such as image derotation, which is an image processing algorithm that compensates for planetary rotation. If you're just shooting normal sequences, for Jupiter, you're limited to maybe 2 to 3 minutes of time due to its rotation, with Saturn 5 minutes and Mars maybe 5 to 7 minutes. So you're quite limited on the amount of time that you have to capture all the data to go into an image. But as I say, with the processing of the image derotation, which I'll talk a bit more about later on, you can actually capture data over a longer time period and combine all of that data to go into one image to create a really nice, smooth, detailed result. So as we move for software for image processing, we have AutoStacker and RegiStacks. Now, AutoStacker, that basically that combines frames from the video sequences into stacked raw files that you could then post-process. And typically RegiStacks is used for, these days, it's typically used for just sharpening the images. It can also stack data as well and produce raw images. But as I say, today it's just usually used for its sharpening features, while AutoStacker is primarily used just for the creating the raw stacked image files from the video sequences. Two more particularly important programs when it comes to planetary imaging. One is WinJupos, and that's a program that use not only for the image derotation feature that I mentioned, but also it's used for the measuring and analysis of amateur planetary images. So it was originally created for actually measuring features on Jupiter, for generating scientific reports on the features within Jupiter's atmosphere. And indeed, it is still used for that purpose. But in more recent times, this image derotation feature was built in, which was certainly a factor in revolutionizing amateur image quality. And of course, we have Adobe Photoshop, which is an essential piece of equipment for any serious astrophotographer. Now, this video sequence you can see here, which was captured with the 14-inch telescope in good seeing conditions, just gives you an idea of what you can see with a large amateur telescope. And one of these video cameras attached under good conditions. You can see there the belts and zones of Jupiter with features visible on the disk, and you can see there at bottom left the great red spot is also visible. But once we've captured all of these video sequences, we then need to process them. And this is where we move the images into AutoStacker. So we're now moving the video sequence into AutoStacker, and that will then run through these video sequences. And you can see here, we've got a sequence of 4,000 frames. Typically what I will do with that is stack the best 50% of frames together, as we need enough frames to give a good enough signal to noise ratio to allow us to be able to process the image. So once we've stacked, say, a couple of thousand frames together from AutoStacker, we can then move that raw stack into RegiStacks. And this part is really the fun part of planetary imaging, as this is where you get to see what all the work has produced. All the collimation, the attention to collimation, cooling, focusing, how good was the seeing. This is where you really get to find out, as when you apply the wavelet sliders, and this is a sharpening routine in RegiStacks. So you can see there I've just applied around 40% on wavelet number 2 there. If I just flick between, you can see that the image contains lots of fine detail visible within Jupiter's atmosphere. And I should stress at this point that it's all of the work before you hit that capture button that really counts. The collimation, the cooling, the focusing, all of those things that come into play. And of course the seeing as well. And that's what will determine how sharp the planetary images will be. I just want to move on a little bit more to discuss image processing and one of the kind of major factors in image quality that a lot of people struggle with, and that's image noise. And you can see here a stack of 1,000 frames of Jupiter in reasonably decent seeing conditions, but you can see the image is very grainy. And this is one thing that a lot of people struggle with in their images is noise. And there are various ways you can overcome this with noise reduction or stacking lots of data together. If I just flick there between the two images, you can see this one with no noise reduction applied. And with noise reduction, it just creates a much more aesthetically pleasing image. I think noise is probably one of the worst things you can have in astronomical images, as it really detracts from their aesthetic quality. And there are various ways you could reduce noise in images. Registax has a function for reducing noise. If you select the Gaussian wavelet option, it will give you the option to apply a certain amount of denoise as well as sharpening. That actually works really well to reduce noise in planetary images. And also the another one that will actually work surprisingly well is the reduced noise feature in Photoshop. Just using a very small amount of that can help just reduce image grain. And there are other more sophisticated programs as well, such as the Topaz denoise plugin, which also works really well to reduce grain noise in planetary images. So moving on, just to talk a bit about weather and astronomical seeing. And as I mentioned earlier in this presentation, astronomical seeing is without doubt the #1 factor which will determine how good your images will be. And it is by far and away the most limiting factor to large aperture telescopes located here on the ground. And you can see here in this basic graph that shows shining away in space, the light being emitted from the star, which is completely unaffected. And of course, the unaffected light waves hit our turbulent atmosphere, which is a churning mass of air, varying in temperature and density. And as the light passes through Earth's atmosphere, it gets distorted, as you can see. And those wavefronts are the wavefronts that we see with our telescopes. But you can also see there how a larger aperture is much more affected by Earth's atmosphere than a smaller one, because you're looking through a lot more air with larger telescopes. And this is why, for example, NASA put a telescope in space. Obviously not so much because it's the perfect dark location, but because it gets away from the degrading effect of atmospheric seeing and turbulence. And that's why Hubble's images are so sharp, because it doesn't have to look through Earth's turbulent atmosphere. And you can also see here, I've put in a couple of images of Uranus, one with adaptive optics engaged, and another with adaptive optics off. And this is with a 4-meter telescope in infrared. And you can see that it kind of really kind of hits the point of just how limited a large aperture telescope can be by Earth's atmosphere. Unfortunately, when it comes to amateur planetary imaging, there are things we can pay attention to, and there are certain weather situations that occur where steady atmospheric seeing is far more likely to occur. And that is typically under large anticyclones or high pressure systems. And you can see here in the left-hand map, which is a surface pressure chart. And you can see there is a big anticyclone there centered over the UK. And this typically always brings the most steady atmospheric seeing conditions to kind of observing sites located in the temperate latitudes. And those are the times you really need to make a concerted effort to get outside and observe the planet, as it's under those big anticyclones that you will always experience the best seeing conditions. And that's for a variety of reasons. But one of the major reasons is because when you have these big high pressure systems in over your site, it pushes away the high altitude jet stream, which can be a really degrading element when it comes to planetary imaging. And you can see here that I've noted various points to consider. There are also some other factors, such as time of day. You can often find better, steadier seeing conditions just after sunset, like the Jupiter images that I showed early on in the talk that I shot at sunset. I've often found good seeing conditions at sunset, particularly here at home in the UK. So there are various points to consider when it comes to seeing. But I think that perhaps the most fundamental one is always make the effort when those big high pressure systems are in over your observing site. Now, not all sites on Earth are equal when it comes to experiencing steady atmospheric conditions. So you can see here a jet stream level map of two very different areas on the Earth. One, the Caribbean tropical latitudes, and you can see there is basically no high altitude jet stream at all, which is ideal for planetary imaging. Whilst there, over Japan during the winter months, a strong jet stream as it sits on the boundary between the tropical air mass and the cooler polar air masses. And as I say, and we also get that here in the UK, and of course you get that in the high altitudes in the United States as well. And the jet stream is a real problem, particularly during the winter months. But as I say, not all areas are equal, and the tropical latitudes are by far and away the most favoured locations on Earth for planetary imaging. Now, if you want to look at the conditions over your observing site and look at the forecast model data, by far and away the best website for this online is windy.com. And this is a really superb weather resource for looking at up-to-date weather model data for anywhere in the world. And it's a really good website for looking at forecast data, gauging when these good periods of weather are likely to occur. So it's well worth checking that website out in more detail. But of course, if you're going to waiting for the night of perfect astronomical conditions, you're going to be waiting a very long time indeed. I think even after all the years I've spent imaging the planets, I'm still yet to see an absolutely perfect night. But one thing I've done over the years to kind of alleviate the frustrations of observing here in the UK is to travel overseas to observe. And it's something that I first started to do in the early 2000s. And it's something I have to admit, I quickly became addicted to when I started to realize just how good the conditions could be in other parts of the world. So I've marked a map here just to show some of the sites that I've spent a fair amount of time observing from over the years. And you can see there's a fair variety of locations, but by far and away the most popular site that I've spent a considerable amount of time at over the years is the island of Barbados in the Caribbean, which is located at 13 degrees north latitude in the tropical Atlantic. And this island is the ideal location for planetary imaging with its low latitude and frequent excellent seeing conditions. And for some years, I actually had to take the telescope with me. And you could see here the C14 packed up with its mount and various other bits and pieces ready for travel. And as I say, this is something I did for some years. I should say considerable success, as you will come to see a bit later on. And of course, the thought of transporting an expensive telescope overseas, particularly if it involves putting it on a plane, just fills people with utter dread, as you know, the chance of it being damaged is perhaps fairly significant. But one thing I did early on is to invest in some really durable, tough, dedicated transport cases. And you can see one pictured there at bottom right from JMI. And I've used this many, many times over the years for transporting various telescopes. And I should say, of all the trips that I've done over the years, and I must have transported telescopes overseas maybe at least on 15 to 20 different overseas trips, I've never had any of them damaged. And I'm convinced that is just perhaps two factors. One, the investment in these transport cases for the equipment, and two, typically this equipment is pretty heavy and it's not the kind of stuff you can throw around like a suitcase. So yeah, I've always had a very good fortune when it comes to transporting telescopes on these trips. And you can see here just one of the transport cases that I've used many times over the years, the JMI transport case for the Celestron C14, which isn't cheap at around $600, but I can certainly say it's probably one of the best pieces of astronomical equipment that I've ever purchased in terms of satisfaction in how it's performed. And of course, observing from some of these overseas locations, such as Barbados, can be a very, very different experience from freezing yourself solid here in the UK winter, where the temperature can be below freezing. So with Barbados, typically the nighttime temperature is around 80 degrees Fahrenheit. So it's a very comfortable and enjoyable observing experience throughout the year. And as I've often said to people, just being outside, observing in the warm, is in itself makes it so much more enjoyable. But of course, nowhere is perfect. Barbados is no exception, with it being in the tropics. It's prone to tropical style downpours, particularly during the wet season. And yeah, you always have to have weatherproof tarpaulins on hand just in case there are unexpected showers. And believe me, they do occur. But as I say, the seeing conditions there are exceptionally good when the weather cooperates. You can see here just a photo I want to include one of the trips we went on when we took several telescopes to Barbados at the same time. And you can see there we've got two C14s, a C11 and a 6-inch refractor, and all the various mounts and pieces included. And it should be pointed out actually that flying all the equipment there and back again, all of it arrived back home again completely undamaged. So again, a real it says a lot for the transport cases that I've talked about. And I just want to show some of the images from recent years as well, from some of the trips to Barbados. So you can see here Saturn from June 2016 with the C14 from Barbados under near perfect seeing conditions. And you can see lots of detail visible on the disk of the planet, such as the polar hexagon around the pole, also some of the ring divisions and some features within the C ring. This is an image from another trip to Barbados 2 years later in 2018, again under near perfect seeing conditions with the C14. You can see a bright storm has erupted around the North Pole of Saturn on this occasion. Moving on, another image of Jupiter from the C14, again under near perfect seeing on Barbados. We can see Ganymede and Io alongside the planet, with Ganymede's shadow cast to the cloud tops. Another image of Jupiter, again from the C14 on Barbados, again under perfect seeing conditions. And I should say actually that during these imaging runs on Barbados, one of the perhaps the most fun thing of all is actually spending time observing visually. So when I've kind of maybe spent an hour or two collecting data, I'll take the cameras off and just spend half an hour looking, as the views of the planets are absolutely incredible. You know, the level of detail that you can see visually through the telescope on objects like Jupiter and Saturn is really incredible. Just to move on to another image from 2018, again with the C14, you can see Ganymede and Callisto alongside the planet with Ganymede's shadow. And this image from 2018 was a particularly interesting one, as I managed to capture Jupiter on almost exact opposition, and you could see Io actually eclipse its own shadow. And this is only possible to capture with the planet very close to exact opposition. So I was particularly pleased to capture that shot. And I think that's the only time I've ever captured that in all of the years that I've been imaging. On to more recent images. This is one of the best images I got of Mars using the C14. This opposition just gone in 2020, and this was taken from my garden here at home in the UK during the night of very good seeing, as I say, with the C14. And with the advent of more sensitive cameras in recent years, we've also been able to start getting good images of more challenging targets. So you can see here some images of Uranus taken with the C14, showing the bright polar area and equatorial band of the planet. And also Neptune is a particularly interesting target for larger apertures. And you can see here an image with the C14 showing a bright storm visible on the planet. And many bright storms have been visible and recorded on Neptune by amateur observers in recent years using near-infrared filters. And Neptune is actually a very active world. Unlike Uranus, Neptune has an internal heat source, so it's a very active planet with storms frequently occurring. And as I said, many of them discovered by amateur observers. Now, of course, the moon is a fabulous target for high-resolution imaging. And you can see here one of my own personal favorite lunar images that I captured a few years back, showing the craters Petavius and Humboldt off towards the eastern limb of the moon under excellent seeing. This is an image of Plato taken under excellent conditions, showing lots of tiny craters across its floor. An image of Copernicus taken under excellent seeing with the C14. And again, the moon is a fabulous target to visit time and time again. And it's something I've imaged extensively over the years. As of course, the illumination on the features is always changing from one day to another. So, you know, they're always fascinating to look at from night to night. Another thing that's been really interesting to try in more recent years is high-resolution solar imaging using C14 at full aperture. And that's done using making a Barda solar film full aperture filter. And you can see here a small sunspot group captured some time back using the C14 full aperture. And you can see all of the solar granulation surrounding the spot. So that's a really fun target to try with large apertures. Now, for those who are interested to know more on planetary imaging in general, and also to get their hands on real data sets to practice techniques, I run a tutorial site on Patreon, and you can access over 100 tutorial videos there, and lots of sets to practice image processing techniques. So for those that want to know more, do check that out. And just to summarize some of the things that I've been talking about during the course of this presentation, obviously a good quality telescope is essential regardless of the type of telescope, and luckily today most of the telescopes that you do come across are of good quality. As I mentioned earlier, choosing something you can use easily and frequently is so important to maintaining your enthusiasm for astronomy, regardless of what you're doing. Obviously, giving the telescope plenty of time to cool down, to reach thermal equilibrium with the outside air, and also paying a careful attention to collimation and making sure you check that frequently. As I showed, making the effort when those big high pressure systems move in over your observing site, because those are the times that are most likely to bring steady seeing conditions. And when it comes to image processing, experimenting with different techniques, there's so much to learn when it comes to image processing. So experimenting and asking for advice is a good practice. And of course, many of the images I've shown, although they're very impressive and spectacular to look at, they're also scientifically useful for longer term study of the planets by organisations such as the British Astronomical Association and the Association of Lunar and Planetary Observers, and also the Juno mission, which is active at Jupiter, are very interested in amateur submissions. And I'm just going to conclude this presentation with animation of Jupiter that I quoted from images that I shot in 2016 under excellent seeing, and I managed to obtain a coverage of Jupiter over the course of a few nights, stitched it all together to form an animation of the entire face of the planet during its 2016 opposition. And yeah, hopefully this presentation will inspire some of you to get out there and observe Jupiter and Saturn on their coming oppositions this summer. So thank you very much.
Wow.
Wow.
That was great. Excellent.
Time for me to take up bowling.
I was thinking the same thing.
Aw.
That's astounding. And how many years? You've been doing this for 30 years?
Yeah, well, I first started when I was 10 years old, so it's yeah, more than that now.
But you started on film apparently then.
Yeah.
Yikes.
Well, we have some questions from the Peanut Gallery.
Okay.
We've got a question from Tom Palakas. Do you use a dispersion corrector for monochrome imaging through RGB filters? Is there a benefit to that?
Yeah, I do use an ADC through monochrome filters, particularly when the planets are lower in the sky. I would say when there are, in kind of the experiments that I've done, I would say when the planets are above 50 degrees altitude, it doesn't really bring any noticeable benefit using an ADC with filters. But when the altitude is less than that, you could definitely notice a difference using ADC with filters.
Okay. Somebody suggested that you go back to the page where you have your URL for the tutorials.
Yeah.
That's going to be a benefit for you and us.
Yeah, we posted, Alex posted that in the chat there. So it is in our chat. I'll put it up on the YouTube link too.
Let's see, I don't see all the questions, so maybe Dan and Alex can say some. Motion Guy asked, why is Hawaii not in your destination list? I would assume because of distance.
That's a good point. There's two reasons. Primarily, one is distance. Yes, obviously it's a major undertaking just to get there. But also, Hawaii is a very mountainous island, and one thing you notice with tropical locations, such as Barbados, and there are other observers that you know of, such as Chris Go, who lives in the Philippines, and others. One key to having very good seeing at the tropics at sea level is you don't want to be near any mountains. So, for example, the Florida Keys, where the Winter Star Party is held, are obviously just, tiny flat islands. And that means that the airflow across them is completely undisturbed. And it's very much the same at Barbados. The seeing at sea level is superb. And it's because the air is just coming across thousands of miles of ocean before reaching the observing site. And it's not disturbed by any topographical features. Now, if you were observing, say, sea level on Hawaii, where you are on the island would, greatly affect the kind of seeing conditions you would experience. And of course, as I say, with tropical observing as well, it's also nice to be warm at night. You're not going to be warm on the top of Mauna Kea at 4,000 meters. So,
Okay, what else do we have here?
Got a camera question.
Yeah, go for it.
Using a one-shot color camera, ZWO, what would you recommend on a C9.25?
probably the best color camera available at the moment is the ASI 224MC. That's one I've used myself, and several other experienced observers also use that camera, and it actually works really well for one-shot color imaging.
Thank you. That's exactly what I was thinking of getting. I wanted to upgrade. I've been using the 120 MC. For the photo.
It's a really good camera for color imaging.
Not that expensive either. It's $250.
No, it's cheap.
Wow.
Well, here's another question then. Do you see any benefit of taking various percentages of images from your stacking run? Like 3K set would pick you up 50%, 25% more. Is that something? The example was to have better, to have fewer but better frames, or more even if a bit less quality of each?
Yeah, it's a good question. The problem is that if you use too few frames of an image stack, you end up with something, yes, that will be a bit sharper, but it'll also be considerably more noisy. So I always err on the side of, typically with the vast majority of my data, I'll typically stack 50% of the frames of the sequence into the stack, because you need enough data going into the image to give you a good enough signal to noise ratio to be able to actually process the data.
Jen, you got one?
We've got a question here. Would you say a C9.25 HD or a C, Edge HD, or C11 standard is better for astrophotos?
If specifically just for planetary imaging, I would go with C11. It's always better to opt for the larger aperture, but because as I say, when it comes to planetary imaging, it's particularly when you get those nights of really, really excellent seeing, you want the largest aperture that you can afford, I would say.
I'm surprised that you say, so the resolution isn't the most important thing on the camera at this point, because this camera you recommend is only, looks like 1300 by 976 pixels.
Yeah, I mean, you don't need a big array for doing planetary imaging, because the planets themselves in the sky subtend only a very small angular size. So, for example, Jupiter's only like 45 arc seconds, Mars, around 20 arc seconds or so. So you're looking at, they're very, very small objects compared to extended objects like galaxies and nebulae.
Because the pixel size on that's as big as the ASI 120. That's surprising. I wouldn't have guessed that.
I wouldn't either. I would have thought that you'd want more resolution to pick up details on small objects like that, but I guess not.
Well, no, I mean, it's with planetary imaging, it's really about kind of matching the pixel size to the focal length. So you are trying to get an image sampling of like around 0.1 arc seconds per pixel. The size of the array itself is really important, because typically, I mean, what you're doing when you're planetary imaging, you're actually using a region of interest crop. So typically, you may only be capturing maybe an 800 by 800 size box from the whole array.
But clearly, the more frames per second, the better.
Yeah.
Is there such a thing as having too much data where you just let it rip and you just I saw somebody talking, I think in YouTube, about that they had they gotten so much data or they saw somebody that had so much data, it just wrecked their computer trying to crunch it all. Is that just overkill?
I don't think so. I mean, if you have a really productive night out there imaging the planets, you can easily come away with a couple of 100 gigabytes of video data.
God.
So
Man.
I mean it does. It so mounts up, it soon mounts up. And one thing you will need when it comes to planetary imaging is hard drives.
So
Yeah, I saw on Facebook that you got a mega terabyte drive to back up all your CDs and drives. Oh man, what a chore!
Yeah, that's I'm pretty much it's still underway at the moment. I've been going for 1 week now, and I'm slowly getting near the end of it.
What are your next plans? I mean, there's so many objects to image, but can you really improve on what you've done already? Is there, other than throwing a telescope up in space, I mean, what's left?
I think with me these days, the enjoyment for me really comes from longer term studies. So with Jupiter in particular, for example, because I've been observed such a long time now, you get to see the longer term weather patterns of the planet. And Jupiter in particular, I think, because it's such a dynamic world in that it can change dramatically from year to year. And it's one of the things that keep it interesting, because from one year to the next, you really never know what you're going to see on it.
And your shots of Neptune surprised me too, because I'd actually never seen pictures like that from the ground, from an amateur astronomer to score that. Is that something that you think that we could maybe be able to pull off in places like Westport, with crappy seeing and bad skies? I mean, is that, if we're patient enough, do we have a shot at that?
Yeah, to be honest with you, I think you'd be surprised actually. And as I mentioned, a lot of the storms that have been discovered on Neptune over, I'd say, probably the last 5-6 years have actually been discovered from amateur imaging of the planet, typically using C14 telescopes. So, if you get good seeing, yeah, very much so, it's possible to catch something. And I should also point out that when it comes to imaging those planets, Uranus and Neptune, all of the detail that they show is only visible in the near infrared. So if you're imaging them, you need to be using something like an IR 610 filter. That's a particularly good filter for imaging those planets. And yeah, I mean, if you get good seeing, you've got every chance of capturing, a bright spot visible.
Here's another question that came in here. Michael Southam is asking, have you really moved away from deep sky objects for any reason, or are you just going to really stick with planetary imaging now?
I think with my own astrophotography, I guess my primary interest has always been planetary ever since I first became interested in astronomy. And I just think it's the kind of dynamic nature of the planets that have always fascinated me. And another thing that I've also spent a great deal of time imaging over the years is comets as well. They're always really fascinating. Again, another dynamic astronomical target. With deep sky, I've kind of forayed into it from time to time. But yeah, it's never been my kind of number one interest within astronomy.
I appreciate that too, because we take some really beautiful stuff, but it's, there's always somebody that's done it before you. And what you're doing is that, you're doing something that really nobody has seen before, with your planets or with a comet or with a supernova or something like that. It is something that is, only visible for that time that you were looking at it. And so, yeah, I appreciate that.
Yeah, I guess that, yeah, it's that dynamic nature. Yeah, as I say, with comets as well, particularly like comet conjunctions with celestial objects, they can be really fun to do. As obviously, they can be a once in a lifetime opportunity.
Anything else, guys? Shannon, Alex?
Not for me. I'm already overwhelmed.
Yeah, and if Shannon's overwhelmed, I'm beyond blown away. This is
Yeah.
just an outstanding conversation, and these images are just magnificent.
Yeah, and let's hit that again too. If you'd like to learn a little bit more and do a deep dive and get some of this data right from Damian that you can process yourself, he's got his Patreon.com Peach Astro, and so check that out. He's on Facebook. He's all over the place, and you can certainly find him and track him down and ask him some questions, particularly if you're going through Patreon.
So I guess
don't know about anybody else, but I'm excited to tell my wife that we have to move to Barbados.
I can't wait.
I'm sorry, David. Well, when I get my boat, we can all sail down there. So I'll be sailing. I'll be sailing all around Barbados for you. Well, let's stick a fork in it. And so again, thanks everybody for coming out tonight. And we'll do this again next month. And don't forget that we also have, for all the astrophotographers out there, Thierry Legault will be here in May. And so we'll ask him, how the heck does he get those crazy pictures of the ISS and everything else that's attached to it? So with that, thank you, Damian. Thank you, everybody, for joining. And we'll see you again next month.
Thank you very much.
Take care, guys.
Nice job. Thank you.
Bye, guys.